So I'll not be very mathematical today. I'm going to try and give the intuitions, because I think the things people struggle with if they've not seen Gaussian processes before tend to be the intuitions and the nature of how you're modeling. So I tend to focus on that. Just a show of hands, who here is familiar with Gaussian processes? Oh, good. Okay, I can go. Okay, so apologies if you've seen. We put videos online. The reason, okay, why did I want to start the Gaussian process summer schools? There's a reason for that. It's every time I give a talk on Gaussian processes, I feel under obligation to, well, I tried to stop introducing Gaussian processes in the talk and not talk about what they were and just talk about issues and extensions. And people always said, well, oh, I didn't know about Gaussian processes, so I didn't really follow the bit after you sort of said, so we're going to use a Gaussian process. That's kind of horrific because they're super general, important models. And they generalize large numbers of models that people use in day-to-day. I'm not going to cover all the different things that they generalize, but certainly I want to cover the way of thinking when you use a Gaussian process. So the idea was to start doing these summer schools, release videos, try and get people to understand these models a bit better, because even if you don't use them, knowing about them and how they work, it can be useful in other areas. So my outline is I'm going to talk about Gaussian processes. So this is still the book. It shocks me to think it's actually really 10 years old, because they do this weird thing where they publish the book in the year after it's actually published. It came out in 2005. And really, the book, before this book, we had a meeting in Sheffield where there were about sort of 15 of us, and that was pretty much everyone in the entire machine learning community who worked on Gaussian processes at that time. There were other people outside that. And we were sort of scratching our heads as to why no one was using Gaussian processes. So they've sort of been like slow burners in terms of, like, Carl and Chris wrote the first machine learning paper on, inspired by work of Radford Neal on Gaussian processes about 1996. So it took sort of 10 years before they wrote a book about it, which explained a lot of the secrets of how you work with Gaussian processes. I still think it's a very good read, although some people say it should be updated, but I can't really tell because I'm not learning Gaussian processes now. So this is like the typical thing I like to show in when I start talks and try and motivate what we're trying to do in machine learning or modeling, because everyone recognizes it. It's y equals mx plus c, and you're immediately thinking, okay, we're going to get some target values, some input values, and we can try and find the parameters. Well, it's a nice thing because it's actually very easy to do, and the nicest thing about it is you only need 2 data points to solve this, because you have 2 unknowns, m and c, so you just need 2 paired values of y and x, and you're there. And we all know this. And actually, one thing that I think is a sort of fundamental thought, which we don't revisit enough when we teach this stuff, so I like to talk about it, is what happens when you get a 3rd data point and what it means to have a 3rd data point. Certainly to give you an idea of what the founders of modeling thought about. And when I say founders, I'm talking about people like Laplace and Gauss, who did modeling way back. Laplace in particular worried about what happens if you've got more data than you have unknowns. And it's worth thinking about what he proposed as a solution to it. There were sort of 3 lines that fit this, and various people at the time said, well, you could take these lines and then you could sort of order the parameters in a certain way and select one set of parameters. They very much believed that there was one set of parameters. But of course, what we actually do, and what Laplace suggested, so this is an overdetermined system, so we've got more points than there are observations. And what Laplace suggested is written out here in French. It's really amazing what he writes. This is on probabilities. He's writing this in 1800. Nous devons donc envisager l'état présent de l'univers comme le fait de son état intérieur. I'm not very good at French, but we can envisage the present state of the universe as the effect of the previous state, et comme la cause de celui que le suive, and the cause of that which follows. So what's that called? Called the no, it's not called deterministic, it's called the Markov property. He wrote this a long time before Markov ever talked about the Markov property. This is a fantastic, if you haven't read this, read it. I mean, it's like the entire, but probably read it in English. We ought then to regard the present state of the universe, the effect of the anterior state, as the cause of one which is to follow. Given for one instance, so this is artificial intelligence, an intelligence which could comprehend all the forces by which nature is animated and the respective situations of the beings who compose it, an intelligence sufficiently vast to submit these data to analysis, computational problem, large data problem. It would embrace in the same formula the movements of the greatest bodies of the universe and those of the lightest atoms. For it, nothing would be uncertain, and the future of the past would be present in its eyes. People stop reading Laplace there and think he was an idiot. He's setting that up as a straw man. That's called Laplace's demon. It's called the deterministic universe. He's writing that and saying, of course, that's ridiculous. We never have that circumstance. So anyone who's sort of doing purely deterministic modeling nowadays is quite a long way behind Laplace's thinking. They get to read that bit up to there. Because, of course, what Laplace goes on to say, so the human mind gives a perfection that has been able to give to astronomy, because, of course, in their day, data was astronomy. Feeble idea of this intelligence, its discoveries in mechanics and geometry, blah, blah, blah. Now he goes on to say the curve, he says, the curve described by a simple molecule of air, so this is before Boltzmann. So Boltzmann had a lot of trouble persuading people that particle theories of air existed, but apparently Laplace was aware of that, or it was a theory before that. Is regulated in a manner just as certain as the planetary orbit. So his first bit, he's talking about planets. The only difference between them is that which comes from our ignorance. Probability is relative in part to this ignorance, in part to our knowledge. So Laplace says that the universe is deterministic, and I think that it's still debatable. I don't know enough about, I can't understand quantum stuff, so let's just say that I'm at the same philosophical stage as Laplace, but you don't even need to understand whether it's fundamentally deterministic or not. What he's saying is that you can't do this because you can't actually describe the curve of every single molecule of air. And of course, what follows this is Maxwell-Boltzmann distributions for statistical mechanics. And that's very natural. We're summarizing the temperature and pressure in this room by the sufficient statistics. That comes after Laplace. But Laplace is sort of saying that you need probability, not because things are naturally stochastic, but because unknown things happen. And he thought a lot about this, and he proposed this as the solution to this problem. I think people don't think enough about this is what they're actually doing when they do least squares. Certainly, he predates Legendre in describing least squares. So you've heard Stephen Boyd talk about the least squares formulation, it's a classic formulation, formulated by Legendre. Laplace is thinking about this challenge as a way of solving this problem. Laplace is thinking about this, and he's thinking about it in this way. He adds to each equation an additional unknown, a latent variable. And that latent variable represents, for him, the difference between what his model is saying about the data, in this case a straight line, and the data that's actually observed. So this is the ignorance. And what does he do with that ignorance? He places a probability distribution over it. Now, ironically, even though he invented the Gaussian density before Gauss, so he also invented it after de Moivre, but he actually invented it for doing Bayesian inference, for doing the Laplace approximation, and Gauss credits him with the sort of invention of that density. Gauss came along later and sort of said, yeah, do this and make the distribution of these variables Gaussian. He didn't call them Gaussian at the time. But he did write a section about how he had this idea before Legendre. This idea that was known to me in Latin. So you see, you can change your languages around if you read this stuff. You can see it all on Google Books. It's really nice to read if you have enough patience to look through different languages. And Gauss, of course, used that to predict something which I think it's a bit of a shame that there's a probe just flown past Pluto, because where's the other probe at the moment? Come on, people. This audience should know. Pardon? There's New Horizons, and then what's the other one? There's Pluto, but what's the other one? It's so sad that Pluto... Is it... what about the Dawn? The Dawn mission? Oh, people. You're depressing me. Discovered, this is not the first time. Oh, dear. No. Oh, people. So, well before this argument about whether Pluto was a planet or not, so the dwarf planet Ceres. Have you never heard of Ceres? Oh, dear. We've been through all this before with Pluto. People learn nothing from history. So, oh, God. So Ceres is, I think, a really exciting thing. These are with the white spots on it and everything like that. It looks like Las Vegas down there. Look at that. There's a gambling planet, dwarf planet, between Jupiter and Mars. Anyway, they found this planet shortly after they found Uranus. And Gauss was the first to predict its orbit. And he used, his claim of priority on least squares is he used least squares to fit the orbit of this planet. And it's so sad that the Dawn is now orbiting that. So we're actually going to get really cool information, or it's about to orbit it. I'm not sure which stage it's at. It had some. So it's a shame that New Horizons has arrived at Pluto, because this is a dwarf planet in the inner solar system, and it's one we can actually visit. It's just beyond Mars. If we're going to Jupiter, we'd have to stop there first and build a new space station. So I think it's a really cool place. It's actually got about the area of Greenland, and it was thought to be a main planet. They called it a Hauptplaneten in these things for a long time. Anyway, that's oh dear. Sorry, I didn't think I'd have to go into the details of that. Okay, so Gauss was inspired by Laplace and used this methodology to fit Gaussian noise here. Now, what's interesting about that is that they're not putting uncertainty in the model. And I sort of think, so this is the stage of which most of our philosophy about modeling, certainly when we teach it, seems to be up to now. Gauss in 1800 when he was 23. Okay, that seems to be pretty much where we get taught to a lot of our modeling. And I think it's a bit sad because Laplace and Gauss were actually themselves a bit more creative than that. And they worried about the case, well, what if you have two unknowns and one observation? So this is now an underdetermined system. But of course, we can solve the underdetermined system by the same thing. We could place distributions over unknowns. So here I placed a distribution over C, and then I'm showing different m's. Now this is philosophically different, and some people find this very difficult to handle because they say, well, this is, now we're putting probability distributions over these parameters. So this circumstance here of having one observation and a linear model with two parameters to fit to it is exactly the same as this circumstance here, because here we've introduced n latent variables. And we dealt with them all, or Gauss dealt with them all, Laplace originally, as a probability distribution. Now what we have in this situation is exactly the same thing. And the right way of dealing with it is to do the same thing. I haven't included the noise here, but we could include the noise. Put probability distributions over M and C. If you want to handle your uncertainty in the way that Laplace described, probability is relative in part to this ignorance, or I don't have the French quote, which is probably better. That's one thing I think is interesting if you read Laplace. I didn't know this. Who here is French? Yeah, so he describes expectation, and in French, what's expectation? Espérance, yeah. And that's like hope, right? And what's despair in French? Pardon? So would it be what would be d'espérance? Would that be, I can't remember the exact words. Anyway, he talks about mathematical hope and mathematical despair in the English translation, which I think is espérance and d'espérance. And he says that mathematical despair is when you have a negative expectation. But I don't know if the term actually comes from him, but yeah, espérance, he talks about expectation and all these sort of things. It's a really modern thing to read, and I suggest you read it, certainly if you like intuitive things. So, well, what's going on in a Gaussian process? Well, we take this to another level. So instead of saying, okay, we're going to deal with this, this object here, which is the separation from what we see and what we're modeling with a probability distribution, we deal with this whole class of functions as a probability distribution. So we have a mechanism for generating new functions. It's an extremely powerful idea. And compare it a little bit to what's going on here. So this is what I think, I took a photo, but I took it of the slide just after Stephen showed this one, which is the classical sort of model's objective function. This is the hinge losses. Stephen showed it last lecture with the regularization. This is what we'd think of as a map type approximation in Bayesian machine learning. This doesn't kind of really exist here yet, but noticeably we have this sum over a number of different values, which is equivalent to an independence assumption about that data, and then we have some regularizer. It's actually very similar to what's going on in this case, because normally you assume that these corruptions are independent. And that's what gives you IID assumptions in probabilistic models. And it's the dumbest thing to ever say about a model. What are we going to assume about our data? I mean, I know this isn't what people really mean, But let's say, so we're going to assume our data is independent and identically distributed. So if the data is independent and identically distributed, okay, for me, all modeling involves prediction of one thing given the other. And the thing I want to predict is I call Y star test data, Y training data. It's very simple. I'm given training data, P of Y. So I have a distribution of my training data, and I have to specify a joint distribution between the test data and my training data like this. So what does an IID assumption say here? If we make an independence assumption, it's the product, yeah. So it would be the product over I equals 1 to n of all the yi's, sorry, P of yi, times the product of all my test data, I equals 1 to n star, P of y star I. Yeah? So what's this conditional distribution? It's just that. It's an independent product across things. So it's not really a model of data. That certainly doesn't model the relationship between y and y star. It's a model of noise. It's a specific model of the way your data is being corrupted. What happens in practice, I've carefully left off the conditioning on parameters. So if we call the parameters W, then conditioned on the parameters, we're saying things are independent. And that's back to that circumstance Laplace talked about in the first place, that things are independent given the parameters. Yeah? So that means that everything we expect to learn about this data has to be encapsulated in those parameters. And I'm totally against that as an approach. I mean, it's convenient, we do it in practice to solve I'm totally against that. Philosophically, totally against that. You know, I'm happy for people to do it when they're doing stuff in practice, but clearly it's not going to give us general AI in any sense or form, and it's really a bad idea when we're in a low data regime. What we really want to do is put probabilistic models that specify this full joint distribution of y star given y. We want to be able to say, what's the distribution over our future test data given the things we've observed in our training data? That's all machine learning is trying to do, certainly if you take a probabilistic perspective. Any questions at that point? I'll pause. Let you digest. Who thinks I'm an idiot? Was that a question or an idiot? No. Yeah? People get the idea. I think learning is very simple, and I think that you write this thing down at the beginning and it's complicated things no end. IID assumption. It's something, actually, why do we do it in practice? Why do we make an IID assumption? Why don't we do this? Yeah.
Because otherwise you can't have any guarantees that future will be like the past, so you can't have any inferences.
I don't think that's right, actually. I think there's a lot of proof about IID assumptions with KL divergences involved, but I'm not sure that you can't have any guarantees in the base case, I would say. It is harder to do proofs if you don't have IID. Yeah, that's true, I'd say. But I don't think I don't think we make IID just for the sake of making theoreticians' lives easier. If that were the reason, we should not do it. No, I think there's another reason. There may be something in what you're saying in terms of the proofs we have, but I think there's another really, really important reason.
So I don't know, let's say in a more computer scientist perspective, the things that if you don't have an IID, then to model stuff, you need the whole history, and it's a very long tail, and it can become intractable.
Non-parametrics, yeah. So it can, in the worst case in Gaussian, yeah, I think that's another point. I don't think it's the right point here. You can parameterize these distributions, so you don't have to store all the history of data. You can store it within certain parameters. So you can get around that, although with Gaussian processes you have to work to get around that. So I don't think that's the actual reason we do IID in the first place, but I think it's a good point too.
So IID means independent and the same distribution, and if we don't have the same distribution, then we probably don't learn much about the current state. And if we don't have independence, we need to somehow also learn the dependence, and people can do that.
Well, people are learning the dependence, and they're learning it by putting it into this modeling part, by having a deterministic part. The y equals mx plus c is learning the dependence. But they're not doing it probabilistically, I guess is my point. And I think there's a good reason why people don't do it generally probabilistically.
So another problem would be also the data collection, because then not only if you collect 10 points, since they're not identical, so since they're not independent, that will translate actually to only one sequence. So So then you would have to collect sets of sequences instead of sets of random points that you get. And then it's harder to train, I guess, because...
Yeah, interesting. I don't think it is harder to train. I think it can be. I'm going to turn that around and say that you can model situations where people do that better if you go beyond IID, where there's batch effects in different sequences. But I think you can still model just as well the independent sequence. Philip, why do you think we don't do IID assumptions more? Why we do IID assumptions more in practice? You haven't been listening.
No, I think it's complicated.
It's complicated. I think there's a really simple reason, actually. So let me try and explain what I think the simple reason is. Model and algorithm. This is a conceptual separation. It's not actually there in practice when we have to do machine learning, but it's an important way of thinking. I've actually been talking about modeling so far. I haven't been talking about the algorithm, how we're going to extract those parameters, how we're going to do the fitting or do the future predictions, how we're going to do this conditioning. IID assumptions make it very, very easy to develop algorithms. If you've got an IID assumption, I mean, you can even do the funkiest, craziest, multiple-layered, multiple-basis function models. You know, all they're doing is making an IID assumption on the noise in deep learning, and everything's in the parameters. W is just some crazy, funky vector. You can do anything with the modeling if you make an IID assumption. So to me, it's about algorithms. You're interested in efficient algorithms that work, and the easiest way to do it is actually to write down these things in the form of an IID assumption. The thing we saw earlier, Stephen Boyd showed us, is giving us a nice convex problem. Actually, Stephen's talk is all about the algorithm side. He didn't really talk so much about the choice for regularizer, why we want, and that's fine, that's brilliant. I mean, it's really important because algorithms are vital, because there's a duality. I'm really interested in modeling, and I kind of think that we don't talk about modeling enough, what we're saying about our data enough in terms of our model. Philip?
But non-IID is still least squares, right? So it's still a simple algorithm.
No, but there's many different non-IID you could do, which is not least squares.
But you could have
Yeah, it turns out that Gaussian processes are relative simple algorithms. So actually, Philip makes this point very well when he does an introduction to Gaussian processes, which you can see online, where it turns out, well, I was going to come to this next slide, but algorithms are in general complicated when you want to do this. This is about non-parametric Bayesian stuff people are doing. You know, any sort of Bayesian algorithm where you integrate over parameters leads to you effectively doing this. In Bayesian learning, it's typically separated in a way that I think is also unhelpful. You typically sort of say, well, we want to do this integral. You see that a lot. That's the prediction of the likelihood under the posterior distribution of the parameters given the data, and you want to do that integral to make the prediction. That integral is just equal to that. But that's kind of more general. It's not necessarily the case that you have to have parameters here. You just have to have a way of doing that. Now, Gaussian processes are a way of doing that whose algorithms are just linear algebra. And Philip really put this very nicely, and is sort of doing a lot of work to show how lots of linear algebra work, which you're going to hear about later, could be reinterpreted as a Gaussian process, which is a really nice way of turning that idea on its head.
Maybe I'll try to difficulty following. So is your argument that the conditional independence assumption that Laplace made is not, it's driven by algorithmic?
Well, actually, poor Laplace and Gauss had to do a lot of work on algorithms. Like, it took 3 weeks to fit the Ceres fit of 60 data. I don't think, no. I wouldn't sort of say when Laplace is doing, I say that's the main reason that assumption dominates. That under that assumption, you can do stochastic gradient descent, you can parallelize your method very easily, you can be very creative about the functional form you choose. So this is this is a deep neural network, right? You know, whatever. You can be really creative about the functional form you choose for that. If you only put your uncertainty there, if you choose not to put your uncertainty there.
Okay.
Make sense?
Yeah, so I guess, so you're saying if you put uncertainty over your parameters, then you're in a better place.
I think if you put uncertainty, well, what I'll try and persuade you is that things get really much more. I'm not saying you have to do this all the time. But I'm saying certainly in regimes where you have little data, then you want to start looking at uncertainty of your parameters as well.
So your argument for assuming a
Yeah, you can. That's another way of viewing it. I don't tend to present it like that, but exchangeability assumptions. So I think this is machine learning all over. Data plus model goes to prediction, right? You get some data and you have to create a model. A lot of people don't spend so much time thinking about the probabilistic assumptions of their model. And I think that if you do, then Gaussian processes seem a lot more natural. So a Gaussian process is just a way of generating Fs. It's a distribution over generating Fs. So you can actually get many Fs from the same thing. And then if you combine them with data, you throw away all the Fs that don't go through your data, just like I did with that straight line before. And that's called the Gaussian process prior, and that's called the Gaussian process posterior sometimes. You can also just think of that as it's the condition, it's the predictions of y star given y. These are the y we're given, and this is the y star we're given. Now this is actually all Bayesian inference is just this. I don't like the term Bayesian inference because it makes it sound like a cult, and it isn't. It's just sensible application of a probabilistic model. I don't even agree that you have to make, people say, Bayesians, they have to choose their prior. Well, so, I mean, everyone, if you're using a likelihood, you have to choose your likelihood. There's no difference between choosing a prior and a likelihood. That's just one way of building a model. That's all. It's a way of building a model. It happens in statistics. They're dominated by this because before people came up with Bayesian approaches, they had likelihoods they used quite widely, and then it looks like you're choosing an extra thing. But we don't have to worry about those sort of things in machine learning because all we care about is prediction. So whether you choose your likelihood or the combination of a likelihood and a prior, you're just choosing a model, a probabilistic model. Now, it can be that you're introducing subjectivity in that, and that's fine. I have no problem with that. In statistics, you have to be careful about introducing subjectivity. So how does this work? Well, I want to just give a sort of an idea of how you can create. The sort of question is, how can you have a probability distribution that's over functions? Because these functions are infinite dimensional objects. So I think the easiest way to think about it is actually to start with something that we're very familiar with. Gaussian processes generalize so many models, like basis function models, large sections of signal processing, Kalman filters, can all be seen as specific aspects of Gaussian processes. Support vector machines can be seen as a particular map approximation to a Gaussian process. So they're a really broad framework. Algorithmically, each of those things is done in a different way. The most general way to do it is quite computationally complex, and that's the sort of thing we face. It's n cubed in terms of data. But that's the sort of perspective I'd like to introduce, because even if you don't do it like that in practice, it's useful to know about that approach. So here's the idea. We're going to just sample from a Gaussian with a particular structure of covariance matrix, and we're going to generate one sample from a 25-dimensional Gaussian distribution, and we're going to plot the points from that sample against their index. So this is my sample. So this is a 25-dimensional, it's not 25 independent samples, and this is the important point. These samples are correlated. So you can think of these as our data observations. And this covariance matrix is giving us the correlation. It's got structure. If it was just the noise, if it was the covariance matrix over epsilon, the noise thing we had earlier, it would just be a diagonal. But because of this structure, this magical thing happens that you actually start to hallucinate shapes of these samples. Those of you who've done Gaussian processes before won't find this surprising, but I think anyone who goes through this for the first time is kind of a bit surprised that you can sample from a Gaussian and get something that looks so smooth out of it. You expect to see something discontinuous. And for many covariance matrices you would. Like if you did independence down here, you would see something discontinuous. I mean, it's only a few that you actually see this type of effect. But I've chosen this covariance matrix. This covariance matrix says that two neighboring points on this is an index now. This isn't my input officially. It's going to become my input. But it's just an index from 1 to 25. And if the sample F1 is not correlated at all with F25. So this is a covariance matrix, but because it's normalized, it's also a correlation matrix. But sample F1 and F2 are strongly correlated. And what I'd like to do is sort of zoom in on F1 and F2 and show you that correlation. So it's these colors here, but it's very, very high correlation, sort of 0.96 correlation. And now the really nice thing about the Gaussian process, and a really important thing about Gaussian processes, is if I want to know the marginal distribution of these 2 points here, so this is the joint distribution of 25 points I have, but if I just want to know the marginal distribution of 2 points, it's trivially found. That's a high-dimensional integral that involves integrating out y3 to y25. Normally that's considered a nightmare. But in the Gaussian case, it's just take the relevant elements of the covariance. I'm not talking about the mean. The mean here was 0. Sorry, I sometimes forget to emphasize that because it's so natural to me that the mean is 0, yet you see something that looks like it's got a non-zero mean. The mean is 0. If I do, it doesn't look like the mean of this sample is 0, but that's because you've seen one sample. If we go back to the plots I showed before, you see, these are the same things, but their mean is 0 on average. Any given sample will never be 0. Any given sample will always oscillate, but the mean of all the samples is 0. So this is one sample like this. So questions about that? I see some sort of consternation. Okay, maybe it will clarify. So what I want to do now is look at what that joint distribution is over F1 and 2. So this is the joint distribution over F1 and 2. It could be either as part of the marginal distribution of F1 and F2, or we could just be projecting down to F1 and F2 from the whole thing. In Gaussians, it's the same operation. That's what's quite nice. Now, what I'm going to do is I'm going to say that I'm going to observe F1 like that. And what I've got here is this is my joint distribution of F2 and F1. F1's off the side there. And this is showing one contour of what that probability distribution looks like. So visually in your head, that's a hill. Right? It's a hill that's twisted towards you. I sort of think of some sort of mountain in a plain, like Uluru, that mountain in Australia, which used to be called Ayers Rock, but it's a beautiful piece of sandstone. And then you're looking, if you're standing at F2, you're looking at it, you just see a bump. Of course, if you're standing at F1, you also see another bump from a different side. You can't quite see this twist on it here. But if you're looking from above, you see that the mountain somehow got a twist, and it's more of a ridge than a mountain. Now, if I observe F1, what I really want to know, according to this equation here, let's say that was my training point F1. I want to make a prediction for F2. I want to make the conditioning prediction of what F2 is given F1. And that's the form it takes. And, OK, so I haven't shown you the maths, and I'm not really going to do the maths in much detail. But conceptually, what it involves is that mountain we built slicing through it. Yeah? And then when you've got a slice through it, you've got some contour along that slice, which you need to renormalize, because it has to be a probability distribution. But that's physically what's sort of going on, is that you condition within that joint distribution, and that puts a line down in it, slices through this mountain, and gives you this sort of prediction for where you are. You're sort of saying, oh, you're telling someone on the hill, I'm at this location here, and therefore, they know the distribution of your heights are on this hill is, it's not the distribution of your heights, is it? But they know that that's the sort of where your slice is. So that's conceptually what goes on. So conditioning on observation of F1, by combining it with this covariance, which is telling me about the relationship between F1 and F2, I get a prediction of F2, which is a Gaussian prediction. And that mechanism is the entire mechanism on which Gaussian process inference is based. That actually doing this process, as Philip said, is relatively straightforward in Gaussian models. This is the form of that prediction. It looks a little bit complicated, but for the example we've shown so far, it's actually quite straightforward. The prediction of F2 given F1 is Gaussian with a mean of, so it's a Gaussian over F2, with a mean of F1, the observation of F1, times K12, which is this term here, the correlation between 1 and 2, divided by K11, which in this case is 1. So that's the variance of K1. So in this case, it's 0.96 of F1. And then the variance is 1 minus 0.96 squared. So this is the variance. This is the original prior variance of F2 minus this variance 0.96 squared over 1. So this thing is like, I can't remember. It's 1 minus 0.96 squared. Now, okay, these prior variances, what do they represent? They represent the marginal variance if you were to look in this direction, right? So if you look in this direction, if you're standing F2, so I always picture, whenever I picture Uluru or Ayers Rock, because I'm British and I can't help but see pictures in the newspapers, it always has a member of the royal family standing in front of it on a visit there. So it's either got Charles and Diana in front of it, or it's got Prince George or something lame in front of it. But ignore them and just look beyond to the rock. You can't actually see how the rock's twisted. All you see is the one edge of the rock is there, one edge of the rock is there. It looks like a rock with standard deviation 1. That's your marginal distribution, and the same looking from this direction. That's the marginal variance there. If we were to remove these other guys, just as we did before, we'd get a Gaussian with a mean of 0 and a variance of 1. That's our prior marginal variance. But the conditional, So the conditional has sort of gone from being a Gaussian, which is variance 1, to a Gaussian and mean 0, to a Gaussian with a different mean and less variance. And you can see that in this equation. You lose variance by making the observation, and your mean changes according to how correlated you are. If you're uncorrelated, your mean wouldn't change. Where that's the correlation, the covariance. Okay? Any questions there? All straightforward so far? So we can do that also with a point that's less correlated. So the fifth point isn't so correlated. If we go back to the plot here, the fifth point, 1, 2, 3, 4, 5, is around about 0.6. It's around the color here. So 1, 2, 3, 4, 5. In this covariance, they're not so strongly correlated. It's still a strong correlation in terms of statistical significance, but it turns out to be a pretty weak correlation in terms of what we want out of a Gaussian process, because this is the form of the new rock. It's much fatter, and if we do this conditioning operation again, we see we've gained much less information. That the new mean is going to be like 0.5 of 0.313, so it's about half the observation now. But in particular, the variance term is 0.5 squared, so it's 1 minus 0.5 squared over 1, which is 0.75, so quite a large variance. So we get a lot less information about F5 than we have about F1. And this is actually interesting because it's true that as the sort of tails go up, you get, well, when things are very tight, a lot of the information in this process turns out to be how things fall away where things are nearby in terms of the properties of the process. There is information over the long term, that's sort of called the length scale, but it's all embedded in this covariance. Now, we can do this for multivariate systems, and this is the general prediction equation we want here. I've not called it Y, because Y is my corrupted data. F is my model, and Y is the corruption away from the model. So this is just conditioning if I observe noiseless data in this case here. These equations are showing me that my, instead of dividing by the covariance of the F, it's the inverse of the covariance of S, so these are now a block covariance. So this is my covariance of my training data. This is my covariance between my training and test data, and same here, transposed, and this is the covariance for the test data. So you have to have, in order to do this, you have to have a way of constructing your covariance for both your training and your test data. You have to build that Gaussian model over Y and Y star right at the beginning, in some way. And then I get this posterior prediction here, which is the full sort of, this is the posterior mean, and then this is the same form as before. If I observe nothing, I just recover the test covariance, but this thing subtracts information away from that. So this is the multivariate form, and annoyingly, this is why we don't, so this all involves linear algebra to do this. It involves building a covariance and then using linear algebra. So it can be easily done on a computer, but annoyingly, these inverses are cubic complexity, worst case, and the storage in n, where n is our training data, and the storage demands are n squared. So the problem with Gaussian processes, this is very elegant and great, but it presents challenge in terms of computation, which is one of the things we try and address. In practice, there are many models that are Gaussian processes that don't have those types of challenges. Like, for example, the Kalman filter is a type of Gaussian process, and it doesn't have these complexities because the inverse of the covariance is defined to be sparse. So there's efficient ways of doing inference in those algorithms, in those models, which are special cases of GPs. Okay. Okay, so yeah, this is the thing we want, the prediction over our test given our training, and it's given by this object here. Now notice at this point I've said nothing about IID. I've just said things about how my training and test data are correlated. And that's what Gaussian processes are all about. It's about sort of saying, I've got pairwise correlation. So it's like the one thing, one step less dumb that you could be with an IID assumption. You're just saying, well, this moment exists. Okay, so where does this covariance matrix come from? Well, many of you will have guessed that they look like kernel matrices. So why do they look like kernel matrices? Because the only constraint we need for this to work, we don't need to worry so much about representer theorems and stuff, as long as we accept this property. See, the point about this property, this is my hand wavy as to why the whole thing works, is I can do this property regardless of how many points are in the sample. So here, let's say I'm trying to look at training data for these 2 points to predict the remaining 23. So if I'm doing that, when I do my inference, I need to take my joint distribution over P of y, comma y star, and divide by my distribution over P of y, which is the P of, here it's F and F star, so let's call it F and F star. Where for me, F is now F1 and 2, and F star is F3 to F25. Yeah? So doing this thing is okay if I can do this for any probabilistic model if I have finite numbers of F. But what happens if in order to compute this, I have to compute this P of F, comma F star, so I'm very bad at working with chalk today, dF star. I have to do this integral to compute this bottom bit here. Now that integral is itself dependent. The result of this integral will be dependent on how many F stars I have. If I don't know my test data at training time, I actually can't do this integral. But for Gaussian processes in general, you can, and it's just this motion here. So that's what makes them processes. It doesn't matter how many points I want to predict across in this function, 25 up to countably infinite. This is still the correct joint distribution for F1 and F2. And that's why we can use them for processes. Okay. So,
Sorry.
question, yeah.
So in the example that you were showing with the sinus function, so the fact that the points are one next to each other, that means that they're sorted through the x-axis is just a coincidence, or?
No, yeah, sorry, I'm just coming on to that, yeah. That was a special, so all the information, so here, in this case, this is the model, the covariance matrix, but I've drawn it in such a specific way, I've aligned things along the x-axis such that neighboring points are correlated with each other. You can do other things, so you can have things like, you can say that points one day apart are correlated with each other, and you get periodic functions, yeah? Or you can say that points either side of the axis are anti-correlated, and then you get things like linear functions. So there's different things you might want to do, but the easiest thing to think about is to say that nearby points are correlated with each other. And if we get the correlation right, the nature of which that correlation falls away, we get this very smooth function. And in this case, it's obtained by, my covariance was actually taken by just putting the index of 2 points. So if the index is 1, then the x location was 1. If the index was 2, x prime was 2. So the cross covariance between x1 and x2 was computed by this function here. Now the point about this is what we call a covariance function, but it's also called a kernel function. It has to, whatever your input to x, it has to lead to a valid covariance matrix. And that means that the covariance matrix, it has to be positive definite. So these are positive definite functions are valid to use. But if you have one of these, what you have is a machine for generating these covariances, for giving you the correlation between any 2 points, where the output is f, or if in corrupted form it's going to be y, but the basic output is f, and the input is x. So you know the correlation between any 2 points as long as you're given their inputs. And anything that people use in kernel methods, you can use here. Oh, cool. Okay, so this is stolen from Philip to try and give you an idea about what these things look like. So Philip will interrupt me if I get the explanation wrong. So what we've done here, in order to try and visualize the sort of functions that Philip had the idea that actually visualizing them dynamically gives you a bit of an idea of what the functions are like, that come from this covariance function, is we've taken a sample from the Gaussian process like we had before. But that sample lives in a really massive sort of infinite dimensional space. And what we're doing is we're taking a circular tour. But think of that infinite dimensional space as just being like, it's got contours which are somehow sort of circular. So think of the globe. Let's think of that sample as one position on the globe, and what we're doing is we're doing a tour around the world to see all the functions that have the same probability of that sample in a great circle of equiprobability. So as you move, each of these functions is itself sample that has a particular probability, and every function you see that's cyan has the same probability. It's like a contour tour around, so like before we had that sort of oval like that, in 2 dimensions, that would be the tour. But this is that tour taking place in very high dimensions. Philip will give a better explanation, maybe even, no. That's that. Will you have these plots in your slides?
Yes.
Yeah. So Philip will have more of these, much nicer, showing posteriors and all sorts. So this is trying to show you that sort of tour to give you an idea of what the nature of these functions look like. So each of these functions is equiprobable across a sort of one of these circles. Okay, so just to sort of you may have seen how to build covariance matrices before, but when we were doing the MLSS in La Palma, Canary Islands, John Cunningham did the intro. I was talking about dimensionality reduction, and he spent a lot of time talking about how you compute this covariance function. And I think he was probably right to, certainly for people who hadn't seen Gaussian processes before, who hadn't done kernel methods before. So I'm going to try and do the same thing, emulating John Cunningham. That's always a good thing to do. So the covariance function is giving us the correlation between 2 points I and j by this object here, which is just a function. And all we do, so if we're going to build a regression model and we've got a training data, so let's say we've got training data with x1 minus 3, x2 1.2, and x3 1.4, all we have to do to build this function is start building this matrix. So these functions have the property that in the argument here, we're looking at the squared distance between the 2 points, right? So this function is basically, if you look at it, the larger the distance is, the smaller the correlation, because it's e to the minus distance. So if the distance is 0, the correlation is 1 times alpha. So in this case, we've set alpha, and alpha gives us a scale over the height of the function. We're setting alpha to 1. So it's a simple thing. It's minus 3 minus minus 3, which is 0. So e to the 0 times 1. But then when we look at the off-diagonal terms, we have x2 is 1.2 and x1 is minus 3. I should have done that the other way around. I had a script to do this, so you don't notice such silly things. So that's 1.2 plus 3, which is a squared, which is 16. And we've got a length scale. The length scale tells us how close is close. So the larger, so if the length scale was infinity, this would always be 100% correlated. We'd actually get flat lines. If the length scale is infinity, all the entries would be 1, and the covariance function is a function over flat lines that are constant at all points. At the other extreme, if the length scale is 0, then actually you start to get noise here. You get everything is e to the minus 0, apart from on this axis here, where you get 1s. And so you start heading towards white noise. But actually, it's all interesting in the in-between areas. So the cross covariance between x1 and x2 is 0.11, and that entry goes up there. x3 is 1.4, so it's a little bit further away. So it's less well correlated with x1 than x2 was. But it is strongly correlated with x2 because it's close. So you end up building these patterns whereby your covariance function says, yeah, okay, given the spacing of these points here, that point is broadly independent from these, and these 2 points are correlated together. Okay? So this is now, we've got obviously points which are not equal distances. If we change, if we wanted to do that, and now, so that's, let's say, our training data. Well, what if we have a test data where the test point is x4 is 2? So now we actually start off, we've already computed this on the previous slide. I've changed, that was 0.995 before, it's just changing the significant figures here. So it's the same as we had on the previous slide. But now someone comes along and says, I have a test point, x4. And what you need to do in order to do testing in the model is you need to compute, in order to get those posterior means and covariances, you need to compute this row, which is the same as this column. So that involves adding in the test point, x4 at 2, and computing in this function the various correlations with every other point. So this is saying, okay, this test point here is strongly correlated with x3 and x2, but not so strongly correlated with x1. So when you make an observation of x3 and x2, you expect your predictions about x4 to be more affected by those than affected by that. Does that make sense? And that's the color of that one. And you can change parameters. So here I've changed two things. I've increased the length scale, so the effect of the covariance is larger, and I've increased the overall scale. So now the overall variance of the function, the marginal variance of the function at any point is 4, as it was 1 before. So it's just a larger scaled function. And I've also, the correlation between x1 and x2 is now larger because the length scale is 5 now, whereas before it was 2. So now I get a bit of a, well, in these regions here, I get a bit more influence from x1 to x2.
How would the, well, maybe this come further, but how would the, so you're explaining how the different values of L would affect the covariance matrix?
And alpha.
What about the different, yeah, what about the different values of alpha?
Okay, let me draw that. Sorry, I mentioned it, but probably wasn't clear. That's often the way with me. Is there a, So if we think of the samples here, they're not signs. It's actually really hard to draw a nice Gaussian. I need practice in that. I don't know. You have to be more relaxed than drawing signs. I guess you get trained to draw signs. So alpha is affecting scale in that direction. And L is affecting scale in this direction. And now you know why alpha is just a rotated version of L. No, that's not really the reason. I only just noticed that. So L is giving us a compression. So, I mean, you can see wherever L appears, it's appearing with the square of x. So it's just a rescaling of the inputs in this covariance function. And most covariance functions have something like this in them, or many have something like this in them, certainly stationary ones. The length scale, which affects, so a sort of longer length scale would just change things out to that, and a larger alpha would change things up to that. Yeah? Now there's other properties of this. Yeah?
I'm a bit confused that x2 and x3 seem to be perfectly correlated in the numbers of calculated. Like we got 4 for the...
That's only given the scale I'm on. Yeah?
Okay.
Just because I didn't want to put lots of decimal places. But yeah, they're not perfect. It's starting, and this is actually an interesting problem. So it's nice that you brought that up. What can happen when you're building, so they can be numerically perfectly correlated. So what can happen with 2 points close together can be such that the length scale is so large that these 2 points are perfectly correlated. And this leads to numerical problems when you're numerically perfectly correlated. Officially, they're not. But this can lead to numerical problems when doing your Gaussian process inference, that you assume, because you end up with these blocks of ones, or numerical ones, which mean that the matrix isn't which mean that the matrix is not full rank, numerically full rank, and therefore it's difficult to invert. So that's nice. Other questions?
How would that look in 3 dimensions? Would it be like extremely flat, or would it be another Gaussian also? Like?
It depends. So in 3 dimensions, what we typically do is we start scaling each dimension independently. So you can do it in different ways. You can do isotropic GPs where they have one parameter, and then they'll just wave equally in each dimension. Or you can do a parameter for each dimension. Scale each dimension independently such that in one dimension it's waving, in another it could be flat. And people call that the ARD prior, very widely used. In machine learning, it's called the ARD prior. It was independently thought of in statistics. They use it a lot. And it gives you an idea of, you have to be a bit careful. It gives you an idea of the non-linearity of each dimension, or the relevance. That's why it's called ARD, automatic relevance determination. So it allows you to do some sort of feature selection. Works very well in practice. Certainly for lower dimensional problems. For larger dimensional problems, you start getting a lot of parameters, and it tends to work less well. Okay, I've got 5 minutes left, so let me just finish off that section there. Yeah, so what I'll... So once you've got those data, let me just show you the interpolation, what you do with the conditioning. So you can now do things like this. So Tony O'Hagan is like, I don't know, the grandfather of Gaussian processes. He did a lot of work on them in the 1970s. He's in stats, and he just recently retired from Sheffield. In fact, I saw him in Sheffield Station recently. And he asked about probabilistic numerics, actually. So that's where Tony's thinking. And Jeremy Oakley's still in Sheffield. Here they're using Gaussian processes for what they call Bayesian analysis of computer code outputs, but is also often known as emulation. So a thing they use Gaussian processes for a lot in statistics is if you have, say, a climate model, and you have a certain output of that climate model given certain inputs. And they use a Gaussian process to emulate that output. And this is what's going on here. So, because we've got no noise, right? So what we're going to do here is show you, so I've got some data, and I'm going to use a particular covariance function, because I've got the input locations and the output locations of the data. I can't remember what the parameters of the covariance function are, and show you the marginal posterior distribution of the mean and the covariance. Important thing number 1. The mean is the average of all the predictions. And I think, actually, Nicola Durand needs to be here to correct me on this, but I think it's the case that you can show that you will never see the mean as one of your sample predictions. Just like before, the mean was flat. It's very misleading, even to practitioners of Gaussian processes who've been there for a few years, when they see something they claim is overfit, because they see that the mean function goes up and then down and then goes flat and then down and then up. None of the samples ever look like that. We'll see an example like that probably tomorrow. And that's really, really important to remember. If you remember that, you're already ahead of 50 to 60% of the people working on Gaussian processes today. The other thing to remember is you can't visualize the full covariance of the posterior here. Well, you can by trying to show some samples from it, but these are just the marginal error bars of the predictions. So, for example, if the real function were actually up here, the next prediction would not be down here, it would be very close to it. So it gives you a sort of misleading impression a little bit. You don't expect, you're predicting like if you knew something was up here, you would know the next bit was close. Because there's no noise in this system. The only uncertainty is that which comes in part from our ignorance. Laplace's uncertainty. This is a deterministic system, absolutely 100% deterministic. But we are ignorant about what's going on between these two parts here. And therefore, we're uncertain. We don't need stochasticity to be uncertain. And I think as we increase the data, we decrease that uncertainty until in this noiseless situation, we even get a collapsing effect. That we seem to even be collapsing to certainty. But as that point was made before, what's going on here is these points are getting so close together relative to the length scale that the model's becoming incredibly confident about what this function does. This is not a good thing. This is a very bad thing. You should never have models that predict with such confidence. But it's actually quite similar to what goes on in signal processing. So if you've known Nyquist sampling theorem, Nyquist sampling theorem can be shown by thinking of the whole system as a Gaussian process. And what you can show is that the covariance function is one that believes only in band-limited functions. So Nyquist sampling says, if we know that no frequency above 100 Hertz exists here, then we know that we can recover the entire function by sampling at 200 Hertz. Something similar is going on here. L is a bit like a bandwidth, so I'm not going into the details of this in our talks, but it turns out that these stationary covariance functions can all be seen as filters in Fourier space. And this filter is a Gaussian filter. And this Gaussian filter in Fourier space is eliminating high-frequency functions. So it's saying, I know, this covariance function is saying that my tails fall off so quickly that I don't expect anything high-frequency to go on, therefore I'm confident about what's going on between these points. Nyquist sampling theory is based on a band limitation, so it's saying there is absolutely no frequency above this. Here, actually, this is not 100% confident, there's some flexibility. But when you sort of think about that, you realize that all signal processing is based on a particular, pretty poor Gaussian process prior. Actually, no one ever uses that in practice, but it's computationally very efficient to use it. That's why they use it. Now I'm going to stop there before introducing noise because we're at 3 o'clock. I took some questions. Do we have time for 1 or 2 questions, Philip? Yeah, 1 or 2 questions. Yeah.
Sometimes in parametrics you want to adjust the bandwidth as you have more data because then you can infer more confidently that the function wiggles a lot and you want to smooth it when you have little data. But it seems like you can't do this if the covariance matrix fixed.
No, you can do that. It's a particular simple choice of... Okay, so a little bit difficult. This is a non-parametric model, so as you get more data, you get, in effect, more basis functions, more power. But you're constrained, the way we've set it up, to that length scale always being the same. But you can do inference over that length scale, and you can put a prior distribution over it, and gain a posterior distribution over it. You just can't do it by linear algebra. You have to go to sampling or something like that. Now, it's quite a complex situation whether you should be... In kernel methods, they would sort of argue that you should make this basis width smaller as you get more data. That's not actually what a Bayesian would say. The Bayesian would say you should use the right value for that or a distribution over values for it if you don't know the right value. But yeah, you can do more complex things than I've said here, yeah. And we'll see about fitting about that next time.
I'm sorry, I didn't understand why this was that case. Can you...
That's because you don't believe in uncertainty. Yeah, a lot of people think, that's great, now we know what's happening. My feeling is no, you've just exposed the flaws in your model. This is my philosophy of modeling. This is opposite to like the bias variance dilemma type perspective, but I think this is the way all probabilistic modelers should be thinking. If this happens, it either means you were right about your model and you're predicting with 100% confidence, or more likely, you're in a domain where you've made a wrong assumption about your model, and your data has now got rich enough to expose that wrong assumption. So my favorite sort of illustration, this is a hand wavy argument, so I'm going to wave hands a bit more with some board stuff for that. This is, if I have one data point like that, I would argue that a linear model is excellent. Because it could be any of these linear models. And we look at the marginal uncertainties, even if this is generally sampled from a nonlinear system, this is probably still going to be quite a good model. It's only when you have two data points that linear models go wrong. Because now you become confident a posteriori that this function is going to go up and up and up and that. And that's when you're in trouble. And I think that that is the way Bayesian should think. But I mean, this is me. I mean, don't accept this as canonical. That if you're ever in the situation that your error bars have collapsed, you better be damn sure about your model. And since I just plucked this covariance function out of a book and don't really have any physical understanding of why this is so, I can only believe in these error bars if I've got serious confidence in my model, which I don't. Because every good probabilistic modeler should happily use these rules, but be aware at all times that their model is wrong. And that's why I don't like it. Yeah? Thanks for that. Just because I've had, no, one for you, yeah.
How would this behave if you have another point in like x equals 0 and f of x equals 3, for example? So you have 2 points in the same value of x.
How would it behave? Philip's actually got really nice plots showing that. Watch Philip's introduction to Gaussian processes from, and then you'll see how it behaves. Really nastily. Yeah, horribly. Yeah, and that's exactly the point. Because you can, actually, first of all, you get numerical problems that will kill you. I mean, basically, you can't even see properly how it behaves. But yeah, horribly. And yeah. But if your numerics is bad, sometimes that's a clue that there's something wrong with your modeling as well. Yeah. One we haven't had from you.
So it seems the crucial property for retractable computation is the marginalization. So are there other classes of models that
Are there other, sorry?
Classes of models?
For the marginalization property, yeah. Yeah, it's true, yes. The question was, the crucial property seems to be this marginalization property. Absolutely, that is the crucial property. I think every class of model that satisfies something similar is a process of some sort. Poisson processes, Markov processes, Dirichlet processes, infinite binary processes. The Gaussian process is one that is particularly tractable. I love that Philip pointed this out so clearly in that same video, that it's just linear algebra to do the inference. But yeah, there are other classes of processes. There's actually, Gaussian processes are a special case of Levy processes. Who's heard of Levy processes? Yeah, so Levy processes cover, like, I think Markov jump processes, Poisson processes, Gaussian processes, and processes that do all sorts of things in between. But annoyingly, the only ones you can write down the likelihood for in closed form are the ones we know about already. So you get these processes that you can show have these properties, but you can't write down the likelihood. You can only write down like the characteristic function of the process, which means it's hard to fit to data. Shall we end there? Yeah, great.